Alright, Space Cadets, so this is Raina and Meg. Say hi to the camera. Meg.
Hi.
So that's Meg, and today we are your black hole experts. So basically, we're gonna welcome you to the world of black holes, so let's begin. So this image is an artist's representation of black hole. Now, if you look at the center of the black hole, that, black dot, well, that's supposed to be the singularity, and it's supposed to be a lot smaller, and all the orangish region kind of spiraling outward from the center, that's the inner event horizon, while as the orange spirals becoming more red, that's the outer event horizon. So this is a very simple diagram of a black hole. The blue dot in the center is the singularity, and the white circle is the event horizon. The singularity is the most densest part of the black hole. That is literally the center of the black hole, and it's extremely dense, meaning it has a lot of matter in an infinitesimally small amount of volume. Now, as for the event horizon, well, think of the event horizon as a point where no return can ever happen. Think of this as a waterfall. So, you and your friend are in a canoe or a kayak, and you're in a river and you're heading for a waterfall, the edge of it. Here's the catch. If you paddle fast enough before you cross the edge, you can still go against the flow of the river and escape. However, if you cross the edge of the waterfall, there is absolutely no way you and your friend can escape. In other words, you're doomed. So that's an analogy for the event horizon. Once you pass the event horizon of a black hole, there is absolutely no return. You're gone. Bye-bye. Also, it's after the event horizon that time and space and the laws of physics, they break down. Time dilation happens. Things just get messed up. They don't look normal. They're not normal. Well, we don't really know, exactly how they are, because thankfully for us, we haven't crossed the event horizon yet. Now, if you were to fall into a black hole and cross the event horizon, you would obviously go faster and faster and faster and faster, getting closer to the speed of light. This causes time for you to slow down. The closer you get to the speed of light, the slower time becomes from you. Now, if someone was to watch you fall into the black hole and pass the event horizon, it'd take them a really long time because time for them is still normal, like right now. So the time difference is time dilation. And this phenomena is caused a lot by black holes, and it's theoretical, but if that were to happen, it'd be pretty practical. Now, if I was to actually jump in feet first to the black hole, a process of spaghettification would occur to me. Now, spaghettification, as referring to the name, refers to a human being stretched into a spaghetti until they are so stretched that they're shredded to their atoms. Yes, this does happen if you were to fall into a black hole. How? Okay, so if I was to jump in feet first, the differences of gravity in a black hole are so immense that my feet would experience a lot more gravity than my head, causing me to stretch. This would be greater and greater and greater and greater the farther I get stretched, and eventually I'd be shredded to my bare atoms. Now, how much time would this take? Honestly, I have no idea, but I think a few seconds, but don't take my word for it because I'm just guessing here. So how do we know black holes exist if we can't see them because they suck in all light? Well, as you can see in the photo, black holes are known to emit giant beams and jets of X-ray. This can be detected by X-ray telescopes. Also, why would galaxies suddenly decide to change their orbits that they have been following for billions of years and change direction? Or why would stars suddenly decide to change the way they're going in and go in the completely opposite or another unusual direction? Chances are they're being sucked in by a black hole, and that's the only chance. So that's how we detect them, or at least that's the raw basics of it.